This is Physics 2212, Lab 6, Magnetic Molasses. So the purpose of this lab was to collect data of a magnet falling through a conductive tube of aluminum foil, model that computationally, and then compare the computation predictions with our observed data. A brief glimpse into the findings is that the experimental time we found to be 1.42 seconds on average, and the computational time was 1.03 seconds. Fundamental principles is first the Biot-Savart law, which just relates a charge or current to the magnetic field it creates. The magnetic field of a dipole, which describes the magnetic field of a bar magnet. Faraday's law, and electromotive force is produced with the change of magnetic flux over a change in time. Additionally, we use the Newton's fundamental laws of motion to accompany those. So for the procedure of the experiment, our system was the bar magnet, and the surroundings were everything else, including the aluminum foil, our phone to record, earth, etc. We assumed that there is no air resistance. We neglected that, and that the aluminum foil is uniformly distributed. On the right there, you can see the conditions that we started with: the tube length, width, etc. And the procedure was first we positioned the bar magnet over a vertical aluminum foil tube, started recording, then we dropped the bar magnet through the tube, repeated that 5 times, and we found the timestamps in that video where the magnet entered and the timestamps that it exited the tube, and calculated the average time that the magnet spent inside the tube, which was 1.46 seconds. After that, we moved on to the computational model, where we began with the initial conditions. At the top there are the constants for each equation, then the length of the tube, the width, the inner radius, and then the outer radius, along with numerical parameters for the simulation, and the properties of the magnet, specifically like its mass and its U constant, magnetic dipole moment. So the first calculations that we did is just defining the bar magnet's magnetic field, which is just this definition at the top here, and then calculating the flux down at the bottom here, utilizing the magnetic field of a dipole formula and Faraday's law, respectively. And then we moved on to the simulation loop, which starts by just defining time and continuously calculates the magnetic force on the magnet throughout the loop until it reaches the end, and then where it updates the position based on the calculations that it found. And finally, the results of this, we can see this graph here that shows the velocity as it goes through the tube, and then on the right here we can see the visual graphic that it shows where the magnet is flowing through that tube. As you can see in the graph here, the time it took is just over 1 second. That's that 1.03 seconds that we found, and that's what the computational model gives us if we plug in the same initial constants that we had for the width of the aluminum foil, the length, the mass of our magnet, and its specific magnetic dipole moment. Some possible errors that could have happened in our experiment is that other magnetic fields, such as the Earth or electronics nearby, may have affected the force on the magnet as it traveled through the tube, as well as human error when taking visual measurements, as we just looked at where the magnet looked like it was starting to go into the tube, found the timestamp there, and then same thing with the exiting. Also, we did not account for air resistance or the friction on the walls of the tube, and there's most likely non-uniform distribution of the aluminum foil. Finally, for discussion, what if the resistivity of the conductor were reduced to as close to 0 as possible? How would it change the dynamics of the falling magnet? Almost zero resistance would massively increase the magnetic current, therefore making the magnet fall through the tube very slow, because that current pushes back up on that magnet and increases the magnetic force. And what if holes or slots were cut into the tube? How would this affect the ring currents in the model? This would disrupt the magnetic force, causing less induction, which would make the box fall, or the magnet fall faster.